First, let's start with the maximal margin classifier. We want to define what a hyperplane is. The xi's lie in Rp, a p-dimensional vector space. A hyperplane in Rp, for some constants beta 0 through beta p, is the set of points x1 through xp such that this equation holds. If p equals to 2, a hyperplane in R2 is a line. If p equals to 3, a hyperplane in R3 is a plane. Let's say that our xi's are separable by a hyperplane, for instance, like this. Now, note that there are multiple hyperplanes that separate our points. So here we have the blue line and also the orange line. They both separate the points. We want to choose our hyperplane such that the hyperplane is as far from each point as possible. Okay, let's make this more precise. A hyperplane, beta 0 plus beta 1 x1 plus dot 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 plus beta p xp equals to 0, is said to be a separating hyperplane just in case beta 0 plus beta 1 xi1 plus dot 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 plus beta p xip is greater than 0 if y sub I is 1, and it's negative if y sub I is negative 1. Okay. In other words, yi times this expression is positive for each I as I ranges from 1 to big N. Okay, it can be shown that the perpendicular distance between xi and the separating hyperplane beta 0 plus dot 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 plus beta p xp equals to 0 is given by this expression here. Okay, so let me write that. So let's say we have a point xi and we have a separating hyperplane beta 0 plus beta 1 x1 plus beta p xp equals to 0. Okay, this is the separating hyperplane. The perpendicular distance between xi and this plane, this hyperplane, is given by this expression. Okay, and here we have 1 over the norm of beta, where beta is beta 1 through beta p. So this beta is not including beta 0. Okay, so the proof of this claim that the perpendicular distance between xi and this separating hyperplane is equal to this expression, okay, the proof of that you can find in an optional video or document titled Proof 1. For a fixed separating hyperplane, beta 0 plus beta 1 x1 plus dot 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 plus beta p xp equals to 0. Okay, for a fixed separating hyperplane like this, consider the minimum distance between the xi's and the separating hyperplane. In other words, consider the minimum of 1 over the norm of beta yi times beta 0 plus dot 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 plus beta p xip as I ranges from 1 to n. Okay, so take the smallest of these distances. This is the distance between the hyperplane and the xi closest to the hyperplane. It's called the margin of the hyperplane. Okay, the margin of the hyperplane. The margin is the smallest of these distances.